All right, now we're on to chapter 10. It's the big stuff now, thunderstorms and tornadoes. What are things going to be looking like with this chapter? Well, we're going to talk about a storm. A thunderstorm, actually, is a storm containing lightning and thunder. Basically, a convective storm. That means rapid updrafts, strong updrafts, moving vertically into the atmosphere. Severe thunderstorms, one with large hail, wind gusts greater than or equal to 50 knots, or a tornado. Ordinary cell thunderstorms are air mass thunderstorms, limited wind shear. That means not much change in wind direction with height or speed. The winds throughout the atmosphere are relatively light. And stages and cumulus are cumulus basically, and convective, and then there's the mature stage, and then dissipating. There's an entrainment, a downdraft, and a gust front. And let's take a look a little bit closer on that. This is what we look at a typical thunderstorm on a sunny summer afternoon. And basically what you're seeing here is the updraft portion, and then the downdraft portion in front, and then more convection in the back side here. For an air mass thunderstorm, we see that we have an updraft. That's air moving upward through the atmosphere. This is warm and unstable air, and it's moving into cold air up above. And then it continues, and we start to get precipitation. As the air condenses, it forms ice crystals and snowflakes, and those bunch together, and they start to melt as they come down into the warmer air, and they form rain. And sometimes you get lightning with this as well, because there's static discharges. And then the dissipating stage, you get what's left called an orphan anvil, and basically just a little bit of precipitation left over. And sometimes these can form sun showers. You don't see much of a cloud, but it's raining for some reason. Then let's take a little closer look. The updraft again, warm air pushing into cold air, warm air rising up, and then cold air sinking, and then cold air outflow, basically gust fronts when it reaches the ground, and then the dissipating stage. So that's our basic average air mass thunderstorm. Once again, updraft, downdraft, and precipitation, gust fronts on the side, and then dissipating stage. And these show up very well under radar under certain conditions. And this is what a maturing, dissipating thunderstorm would look like over the ocean per se, or over a large body of water. And we can see through them sometimes, and we do get sunshine. Thunderstorms, multi-cell thunderstorms, thunderstorms that contain a number of convective cells, each in a different stage of development, moderate to strong wind shear, or they tilt. They tilt. The thunderstorm is leaning, and they overshooting top. That means a very unstable air mass. Gust front, leading edge of the cold air, outflow air, shelf cloud, roll cloud, outflow boundary. These are all things that are common with a gust front. And then we also have microbursts. This is localized downdraft that hits the ground and spreads out horizontally in a radial burst of wind and wind shear, or virga. And here's what we're looking at again. What we have multi-cell thunderstorms, updrafts forming, and then we have hail in parts of these. That's what that white stuff looks like right there. That may be hail, or it's just sun shining on the rain. But this is a multi-cell stage thunderstorm. It's not an air mass thunderstorm. They lean, they tilt, and they can show up on the radar as seeing, and you can see the leaning and tilting on the radar. Here's a little better look at the diagram. You have wind shear up above. In other words, winds increase or change direction with height, and this causes the storm to lean. And what was producing the updraft here is now leaning back, and the precipitation falls away from the updraft. And that means the updraft can be maintained. New cells continue to develop. And then you get, once again, a strong downdraft that can produce the outflow. In an air mass thunderstorm, this would be a ring around one cell. You don't see multi-cells. In a multi-cell system, these would be merged together and forming in a line like this. You get a shelf cloud forming where the downdraft is pushing warm air up ahead of the thunderstorm. You also get a roll cloud forming. So there's organization to this. This is not what you would call a isolated cell thunderstorm. This would be an organized line of thunderstorms. Here's what it looks like on the radar. You get this line of thunderstorms producing, and this outflow boundary here, you're seeing this outflow boundary forming along, would probably actually continue because the center of the radar is right in here, or very close to this, and the radar beam is overshooting it because it's so close to the ground. But you're likely getting a gust front all along this line of thunderstorms, and this would be a multi-cell system. For a dry system, a very dry single cell thunderstorm, the precipitation may be evaporating before it reaches the ground, in which case you get a microburst like this. And this is what a microburst looks like. Now, aircraft flying through this is what they would experience. Say a jetliner's flying through and hits the updraft or the downdraft winds as they hit the ground, gets a strong headwind. The pilot compensates by decreasing power because he doesn't want to fly that high, and the result is when he hits the other side, he's going to lose altitude. He's lost all his lift, and he crashes into the ground. This is very common around Denver. We've had many aircraft accidents, but fortunately, in the last 10 years, we've had very few of them, if any, due to microbursts because we have had an aggressive training program for pilots, and also we are aggressively watching out. We know what causes them. Again, let's review. The airplane flies into the updraft and cuts back on throttle and then flies over the other side and crashes. And that's what we have with a microburst, causing wind shear that causes airplanes to crash. Thunderstorms, multi-cell thunderstorms. We have squall line thunderstorms, a line of multi-cell thunderstorms, prefrontal squall line, a derecho. And we had that happen last summer. A big one moved through the D.C. area. Mesoscale convective complex is a number of individual thunderstorms growing in size and organization in circular convective weather system. And they're common during the summer, and they go more than 10,000 miles in diameter. This is a squall line. This is a line of heavy thunderstorms, and sometimes you get light rain falling behind them, but basically a line of strong thunderstorms, and this would be across Indiana, southern Illinois, and down into parts of past Missouri into Arkansas. So it's over many states, all the way actually from southern Michigan down into Arkansas. So a large, long line. Sometimes these form ahead of a cold front. You get a cold front, say, moving across parts of Kansas and Oklahoma, but this may be way out in front over Missouri. You get the airflow up above gets a little bump in it, and that will cause instability and force the air to rise ahead of it. And then once you get those thunderstorms running, you get a strong updraft. This cold front or cold air mass pushes out. You get strong straight line winds, maybe damaging winds, but they're forcing the air to rise. And then you get what's called a rear inflow down jet, and that's heavy precipitation being forced down. And this is often what you get forming when we call it a mesoscale convective complex. This would be over Missouri. Here's Kansas, Oklahoma, Arkansas to the south. And sometimes you get a derecho forming with them, very strong, severe thunderstorms ahead of that, and a bow echo and a loop, but a mesoscale convective complex. This whole thing could be rotating. Here's what it looks like from outer space, just a blob of thunderstorms with some extremely cold tops showing up on the infrared. But notice the absence of any thunderstorms anywhere else, just sort of a big blob that forms right over the plains. Very heavy rains and produces a majority of the summertime precipitation, especially in Missouri, Iowa, Kansas. We had an absence of these last summers. That's why we had the drought. Thunderstorms. Again, a supercell thunderstorm. Let's talk about that. Large, long-lasting thunderstorm with a single rotating updraft. Strong vertical wind shear. In other words, changing wind direction with height or speed. Outflow never undercuts the updraft. Classic high precipitation and low precipitation supercells. There's different ones. And then we have what we call a cap to the convective instability, and that cap is what provides the rapid rising air that is common with supercell thunderstorms. Rain-free base and a low-level jet. Surface wind speeds change with height, and we have conditions throughout these different heights that produce wind shear. Here's what we look at when we see a low precipitation supercell. The whole supercell is rotating, and it's rotating counterclockwise, and at the center of that is a tornado. This is a rotating thunderstorm, and at the center of that rotation is a tornado, because as this rotation moves up through the atmosphere, it's like an ice skater pirouetting on the ice or making a spinning motion. As she becomes thinner and taller, what happens? She spins up. She gets faster and faster, and that's what happens here at the center of the thunderstorm. Here's what I'm talking about. We have this updraft that's being produced by the convective cloud, and as I said, as air moves into this, it spins faster and faster and faster, and then it gets tighter and tighter. It produces the tornado. Again, here's wind shear with height. Wind speed increases with height and gets the storm leaning. Here's a look at the rain-free base. This would be what I would consider a wall cloud, and we'd have to watch this to see if it could eventually produce a tornado. Here's again what we're looking at with the weather conditions as we look through the different layers of the height. At the surface, we get warm and humid air, a low-level warm jet moving in perhaps off the Gulf of Mexico. Up above, you get dry air and cooler air moving in, and then a trough of low pressure moving in from the west. This is up in the upper part of the atmosphere, but the wind is changing direction and speed with height, and this causes the thunderstorm to lean, and it also causes the rotation. Thunderstorms and dry line, a sharp horizontal change in moisture. We talked about that in the different air masses. Floods and flash floods often occur with these, such as the Great Flood of 1993. We had a dry line, but in the East Texas area, warm, moist air. Here's the low pressure over Oklahoma, and this was the result, a big flood in 1993 from that precipitation in the Dallas area. Thunderstorms, Big Thompson Canyon flood. 12 inches of rain in the 4 hours created a flood associated with $35.5 million in damage and 135 deaths. This was back in 1976. Another big flood that happened was in Rapid City, South Dakota in 1972, and that one killed over 200 people. And again, 16 inches of rain in about 6 hours fell west of Rapid City over some steep canyons, and that flood rushed through Rapid City, South Dakota. Distribution of thunderstorms, most frequent Florida and Gulf Coast, Central Plains, fewest Pacific Coast and interior valleys. Most frequent hail is in the Central Plains. Here's what we're talking about. Most frequent lightning strikes. Florida, look at that, over 90% of the lightning strikes occur during the summer, and very common strikes 90 days out of the year and over 100 days a year right around the Lake Okeechobee area. And about 50 to 40 days per year get thunderstorms, and it decreases with that and decreases out west as well. But hail, look at this, the number of days with hails. You get over the western high plains 8 days typical with hail here in the Three Corners area of Nebraska, Wyoming, and Colorado. Then out over the higher plains again around the Salt Lake City area, another bullseye, but much less hail as you get into the eastern U.S. and virtually a little bit more actually as you head out over the west coast. You get some hail due to some cold air aloft producing them, but not usually with thunderstorms. Lightning and thunder. Lightning discharge of electricity, and thunder is the explosive expansion of the air due to the heat from the lightning. So the lightning is producing the thunder. It's not clouds bumping into each other or anything like that. Thunder comes from the lightning. Electrification of clouds. Here we go. We see the static discharge. You get ice crystals forming on the upper part, and that releases static discharge. Here's a little closer look at warmer hailstone, but you get a negative charge around the hail. Then ice crystals, as they bounce off it, produce a positive charge. So you get a distribution of charges in the clouds, and that creates a positive and negative charge, some positive scattered throughout, and it's got to balance out the charges. So you get lightning. Types of lightning, you get blue jets, red sprites, elves, lightning strokes, positive charge, stepid leader, ground stroke, lightning, ribbon lightning, bead lightning, corona discharge. Here's a little bit closer look at when we get these discharges to the ground. They come through the cloud and reach the ground, and sometimes you get a little bit of a leader that comes up to meet the lightning halfway. Little closer look, boom, big lightning strike, that's the thunder. Here's a little colorful look at it. See the massive updrafts with the thunderstorms, the air rising through, and then you get the lightning forming all underneath that. Top of a flagpole may look like this when the static starts to get really high. I've been in a situation in a boat, not a place to be when you have thunderstorms around, and we started to get that static. We bailed out and got out of there just in time to avoid getting struck by lightning. And then lightning again, here's a lightning rod on a house, deeply buried in the ground. Oops, backed up one. Lightning hitting the pavement. You can see it can do damage even to pavement on the ground. Lightning detection and suppression. We try and have lightning depression and set lightning detection network and suppression. We seed the clouds with aluminum actually. That is not done very much at all, but we do try and suppress the lightning with lightning detection systems as well. Do not seek shelter during a thunderstorm under an isolated tree. That's asking for trouble. Here's lightning discharged around the planet. You can see how it's mainly over the continents, just a little bit of lightning over the oceans, not very common there, but you can see a big bullseye here over Africa and parts of South America. Rapidly rotating tornadoes. This is going to be a fast move, rapid rotating column of air. Tornado currents, want to get to these graphs. So in other words, big currents of tornadoes. Here's Tornado Alley. And the number of tornadoes, big months of the year. The warmer months, of course. And the rotating column of air, multi-vortex system. A massive tornado here, large tornado system. tornadoes per year. Again, a decade. I'm going to get to these graphs here. Here's showing the rotating column of air, and you can see it's a horizontal rotating column of air due to wind shear. Gets tilted into the thunderstorm.